Welcome back. So I next want to discuss how to conduct IFDS by drawing the exploded supergraph for this simple taint analysis example. And I've shown you on the previous slides how to conduct, how to basically encode individual flow functions for a given statement in IFDS. But now we here want to do that for this entire program. Granted, it's not a large program, but it's just to get you started and to explain the idea. And what's really nice about IFDS is that these transformations that I showed you, so how to come from basically a flow function to a graph representation, that is really compositional. So you can really do this for each and every individual statement in the program linearly, and you don't even have to do it, well, if you don't want to, you don't have to do it one statement after the other. You could even parallelize this, right? So you could create these statement level subgraphs in parallel for every given statement. And then you just need to compose them. That's really all you need to do. So you would do this transformation for the first statement, second, and so on, and then you simply compose these graphs together. And basically, for this particular program, you would have a control flow graph that looks like this, right? So we here have this main procedure, which is calling foo with x as an argument that is here mapped to a parameter p, and then we have a return. And now for all these different values, so 0, the tautological 0 fact, and x and y, we have these exploded supergraph nodes here, but we also have exploded supergraph nodes for 0 and p for the call-e procedure. And now the only question is, how do you need to draw these edges? How are they correctly drawn? And I will give you a couple of minutes to work on this in your own time. So if you want to do this as a little exercise, I encourage you to stop the video now for maybe 5 minutes or so and see if you can get your head around this and how to draw these edges. And then we will get back and I'll explain to you how it's done. Okay, welcome back. I hope you had the chance to actually complete this example. So first, let's take a look at the first statement. So I'm going to do this in order. So first of all, what we have here is a so-called normal flow function. So that means this flow function is actually modeling an intra-procedural control flow. And in this case, we have the situation that we have a source, right? So we want to unconditionally taint x. And like I explained earlier, this is done by drawing such an edge from 0 to the fact that represents this variable, right? So from 0 to x here. And I'm not drawing an edge from x to itself because the previous value of x is actually killed. But here it doesn't really matter, right? I could have drawn it, it wouldn't change the result because no matter what, x is going to be true here anyways. Then for the second statement, if y were holding a tainted value earlier, now it's not holding one any longer, right? So we know, looking at this program, that y was never tainted. But we only know that because we know the entire program and we can look at it. But if we assume that these data flow equations here or their graph representations, they are created one statement after the other without considering any other statements, then it might have been the case that y was tainted earlier, right? And then this taint would be overwritten by 0, and then this taint would need to be killed. That's why you do not see an edge here from y to itself. So this is saying in case, just in case, y was tainted earlier, now it's not tainted any longer. Now we come to the call to foo here. And now next we would process a so-called call flow function that is mapping from the caller's calling context to the callee's calling context. And it will map 0 to itself because 0 is always true. But in particular, it will also map the the actual parameter x to the formal parameter p that we have here. Then again, we are conducting a normal flow function here. So this is again the same situation as here. We are killing p. And now we are processing this return. And now this corresponds to the call flow function. So we have a corresponding return flow function, which again implements a parameter mapping. 0, it's still always true, so it's being mapped onto itself. And p this time is mapped onto y, right? So this is the y column, because here the return value of foo is being assigned to y, right? Had it been assigned to a different variable, this would go to a different node. Last but not least, we have another normal flow function here, right? And yes, this print statement, it might be a sync, so this flow function here might actually have some side effect that reports a result here, for instance. But other than that, in terms of the data flow equations, this statement will have no effect. So here we are using actually the identity function. But now take a look at this program, and let us assume we would have something like you see here. So let us assume we had not printed y, but we instead had printed x. Okay, nothing else changed. I just changed this parameter down here. And take a look at the program, right? So we are actually tainting x. Then we are passing it to foo, but that doesn't really do anything to x. And then we are printing x. So certainly x is tainted down here. And we want to report that as a taint analysis result, right? But now if I take a look at whether or not the data flow fact x at the statement is reachable or not, I have a problem. That is the data flow fact x, right? So that is the node that represents this fact. And clearly it's not reachable in the graph, right? So what happened here? Take a look at this example for a minute, and in particular, take a look at this function call here. So we did process this call flow function and the internal flows here, and then the return flow function, right? But somehow we forgot something, namely there are also internal data flow assignments that have to be processed on the side of the caller, right? This is because the call to foo, it doesn't really change anything with respect to x. And also actually, well, it does change something with respect to y, but not with respect to x. But here we neglected to sort of keep alive the value of x, right? So we did not put any sort of edges here. And therefore, basically, x is killed, although it shouldn't be, right? Because this procedure call, it has no effect on x. And so what we're actually missing here is what in the IFDS paper is called the call to return flow function. So there's not just a call flow function and a return flow function, there's also a call to return flow function. And if we add this function here, it looks as follows, right? So it's keeping 0 alive because that is always true, but it's also keeping x alive and reachable because x is not changed here. It is killing y because y is being overwritten here, okay? So that's important. You need to have all these 4 classes of data flow functions. You need to have the normal flows that propagate intra-procedural flows along non-call nodes. Then you have call and return edges, but you also have call to return flow functions that propagate intra-procedural flows over call nodes. And most often this is simply the identity function, but as you saw in the example I just showed you, if you have a situation where for instance, a return value is overwritten, then it might look slightly different. Or you might also have a situation where you actually pass pointers as arguments into a procedure call, and then the callee procedure, it might even strongly update information about some data structures that can be accessed through these pointers, right? Or in Java, they can also be object references. And in these cases, you also need to be careful with using the identity function as a call to return flow function, because then in these cases, values can really be overwritten, and your call to return flow function should account for that. Now, what I presented to you so far was this idea that you can really create these different functions or these different graph representations for these functions individually for one statement after the other. And I said you could even parallelize this. You can do it in any order. But the problem is that this also gives away some optimization potential. In particular, this would compute certain edges that go out of certain nodes that are not actually reachable from the program's entry point at all, right? So if you knew reachability information ahead of time, or at least you can also compute it on the fly, then this might actually save you some computation time. And in general, pre-computing the entire exploded supergraph for a program might even be prohibitively expensive because the program might just be huge. And so the idea is behind the following, which we and also the authors in the paper call an on-the-fly algorithm. The idea is just to compute only that fragment of the graph that is actually reachable from the statement S0 and from the tautological fact at the statement, right? So anything that's reachable from there, we compute, and the rest we simply omit because we know by definition it's not going to be reachable anyways. So there's no need to compute it. Also, I want to explain to you another aspect that is important to IFDS, because IFDS, it's a summary-based approach, it's a functional approach, like I already explained earlier. So we want to store procedure summaries once they have been computed for a certain procedure. And I will now go through the example that we initially had once again, and I will explain both of these aspects to you. So the on-the-fly computation, but also the summary computation. So at the beginning again, we are starting at the initial statement. So let's say this is S0, and this is the exploded supergraph node representing the zero fact at this statement. And now in order to be able to compute these summary edges, we will again build longer and longer summaries. You already saw this when I was talking about the functional approach. So we will do basically the same we did there. We will again start with an initial path edge that is simply a self loop. So this is saying the target node, namely this node, is reachable if and only if it's reachable from the source node, which is the same node, right? So this is just a tautology. It's saying this node is reachable when it's reachable. And we know by definition that it is reachable. But now, given that this is a reachable node, because it has such a red edge pointing to it, we now compute the data flow function. And we already saw that it looks like this. And now again, we compute another set of summary functions. And that basically means I will take the target of this red edge, I will follow the flow function edges, and I will draw new red summary edges that go to these targets. They look like this. So this is now saying, because I previously knew that 0 is reachable, I now know that these nodes are reachable as well. I again compute the flow functions. They still look the same. But now also I further extend the summary functions or summary edges. And in the paper, they're also called path edges because they actually summarize data flow paths through the procedure. So this is now a summary that summarizes everything that's happening from here to there in the program. And this is telling us we now know that X is reachable because X is tainted. And we know that 0 is reachable, but Y is actually not. Okay, that's implicitly encoded by not having an edge. And now we will process the call flow function. So this makes parameter P reachable here, right? And now you might think, okay, now naturally we do the same, right? So we will draw an edge from this node to P here, but we won't. Instead, we do this. So let's take a look at this. So again, we use the flow function that is defined for this call statement to map the parameters to the formal parameters that we have here. Okay, so actuals to formals. And we map in particular X to P. But now we do not draw an edge from 0 here to P. Instead, we draw such a self loop. Now, why is that? The reason is that the summaries that we want to compute in the end, they should be procedure summaries for this given procedure that we are summarizing. But these summaries, they should ideally be independent of any particular calling context. So that means a summary I'm creating here for this main procedure, it should, it should hold for anything that's calling main. And a summary that's created for this callee procedure, it should hold for any call side that is calling that callee here, right? That's the entire purpose. I mean, we want to create summaries so that they are reusable across different call sides. And if I now were to draw such a summary edge from that particular node here, that it only has a meaning in that particular setting for that particular call side to P, that would bind it to that call side here, right? But we don't want this. And so here we, again, instead, create such an initial self loop. And this is basically saying P holds in any calling context in which P holds. So it's implicitly quantifying over calling context. It's not naming a certain calling context or not even a set of calling contexts. It's implicitly quantifying over them. It's a little bit similar to Vasco, where we also had these summaries that said, I don't care about a particular calling context, but if it has this input set, I know what the output set is, right? Or if I have this input mapping, I know what the output mapping will be. And so that's the self loop that we have here. But then again, we do the same, right? So we look at what's reachable here. We compute the flow function for that particular statement. Now here, this will only make 0 reachable because P is actually being killed. But now we have here reached the end of this procedure, right? So we have reached the end of the callee procedure. And now, therefore, we will actually be creating a procedure summary. And the summary here, it basically looks like this. So the flow functions obviously go away. We can also throw away the self loops. They're not interesting. We are only keeping in memory the edges that go all the way from the top of the procedure to all the way of the bottom of the procedure. And this gives us the summary edge in this case. And then we need to map this summary into the particular callers context that we have here. And this is again done by looking at the return flow function. So here it's very simple, only this node is reachable, so we only map this to itself. And then again, we are now looking at the callers context, right? So because of this edge here, we have just made reachable this node here in the caller. And this means that in the caller now, because this node has become reachable, we are again drawing such a path edge here. Okay, so the path edge is actually now going to this node. So it's again a summary that is intra-procedural with respect to this particular procedure here. And then because of the call to return flow function, actually also this node here becomes reachable, right? And then we continue doing this, right? So again, we said we have an identity function here. So this is actually being propagated further. So in the end, even these two nodes would become reachable. And then a procedure summary for main would actually have these red edges that go from here to down there and down there. But something that I want to point out now is the following. So first of all, we were able now to compute these summary functions, which is nice. But also secondly, if you now look at the flow function computation, so the solid edges that we have here and also there, and you compare them to what we had earlier in the approach that was not on the fly, then you will see that these purple flow functions in the on-the-fly algorithm were actually never computed, right? So in particular, in the original approach, you would have computed an edge from Y to Y, because why not, right? I mean, Y is not overwritten by this statement. We would also have computed this edge and this edge and this edge, but all of these are actually unnecessary because they're not reachable from this node here. Okay. And that's exactly why they can be omitted, and that's also why the on-the-fly algorithm will not compute them. So the drawback of the on-the-fly algorithm is that it runs sequentially, right? So you have to start at some well-defined starting point of the program, and you bootstrap everything from there, and you only compute what is reachable from there. But the advantage is that you really only compute such a fraction of the exploded supergraph. And that's what I wanted to say about the on-the-fly algorithm. After the next break, I will talk a bit more about summaries and what effect they really have in IFDS.